Now, in this video, I just want to play around with Lagrange remainder and really just test out where this concept can be applied, right? First, to introduce what the Lagrange remainder is, it's basically given by this formula evaluated at a specific value of x, okay? This is not a function, it's a formula for finding the Lagrange remainder. It's often known as finding an error when we're approximating a function using a Taylor series. And an important thing to note in this formula is that here we have a value of c, right? Usually when we're dealing with Taylor expansion, in the argument here, we would have the value of a, right? And in Lagrange series, the value of 0 would replace a here, right? And here. And we would center the function at the value x equals 0. However, this is not the case here. Instead, c can come from a range of values between a and x. All right. And why is that? Because in order to find the maximum remainder, right? In order to find the maximum error, what we need to do is go through all the points between a and x and find the value that overall provides the maximum output for the remainder, right? And if we wanted to make sense of this using the Taylor series for a function, basically we know that f of x, basically the Taylor series can be used to approximate f of x if we have a finite value of n, right? Sometimes for certain functions, if we have, let's say n equals to infinity, then f of x will be equal to that Taylor series. However, for finite value of n, what occurs is that f of x is equal to that Taylor series plus a remainder. And again, as I've noted before, the remainder is evaluated at a certain point, at a certain value, right? If we're evaluating a function at a certain point, then yes, we can use the Taylor series to approximate the value. And if we wanted to find the remainder, then we would use the same value that we used for x to find the remainder or the error. And in this video, what I want to do is combine the concept of matrix exponentials with the Lagrange remainder. Now, anyone who has dealt with matrix exponentials should know that we can actually use Taylor series to approximate f of, let's say, a matrix, right? So instead of an arbitrary value of x here, we can actually have a matrix for the argument, and we can actually use the Taylor series to approximate this function of a matrix. And let me show you how it's done. How the concept of matrix exponentials can be combined with the Lagrange remainder. I want to show you another cool way of finding the remainder or the error. It's the Taylor inequality, which is also sometimes called the Lagrange error bound. And basically, this is very similar to the Lagrange remainder, with the exception being here is that to approximate the remainder, we're bounding the n plus 1 derivative of f of x, right? We're bounding it and trying to find maximum value, which is represented by n. So basically, if you just get rid of these absolute value signs and say that n is equal to this right here, it would just be the remainder, the Lagrange remainder. However, another thing to note here is that x minus a must be less than or equal to a certain distance, which means that the x must also be bounded, right? It must be within a certain range. There's a good reason why, because when we're trying to approximate a function, right? Let's say we're trying to approximate a parabola and we find the Taylor approximation for it. When the Taylor approximation is centered at a certain point, right? near or surrounding those points, those neighborhood points will have a value closer to the function, but as you go far away, the remainder increases, right? And so really finding that maximum value can really help us identify the error of the approximation, the Taylor approximation. Now, uh, keeping that aside, coming back to our main goal of this video, which is to combine Lagrange remainder with the matrix exponentials. To show you guys how we can do that, what I want to do is show you guys a problem right here, which is what the problem states, finding the first three terms of e to the power of a using the Maclaurin series of e to the power of x. And after we find that approximation, what we need to do is find the Lagrange remainder of a. Now, how would we do this? Oh, well, first of all, to let you know, to inform you guys, A is actually equal to this 2 by 2 matrix. I kept things simple for this video because I didn't want to make the computations too harsh, because already we're going to be dealing with some complex stuff, and we're not making the computation hard will just make our lives miserable. So for the sake of simplicity, I just picked a 2 by 2 matrix. But moving on, in order to find the first three terms of e to the power a, that's the first part of the problem. What we can do is just use the Taylor expansion, uh, the first three terms of the Taylor expansion, right? Now in Taylor expansion, you're used to seeing the variable x in Taylor expansion. Here we see the matrix A. Now this is not, here we're not breaking any rules. We're just replacing an arbitrary value of x with a matrix A. We can do that, right? We're not breaking any rules. However, an important thing to note here is that in the Taylor expansion, instead of this identity matrix, we have the value of 1. However, the reason why there's no 1 here is because if there was a 1 here, then this operation would not be possible, right? We cannot add a number, let's say 1, with a matrix, right? We cannot do that. So instead of 1, we just replaced it with the identity matrix. Now, this approximation here, which kind of values to this and evaluates to this matrix right here, right? So this is the first part of the problem. Pretty simple, nothing too fancy. However, now we have to find the Lagrange remainder. This is where things can be challenging. So if we recall the formula for finding the Lagrange remainder at an arbitrary value of x, that is between a and x, with k being between a and x. Let's just say, since here I know k is supposed to be a value that would provide a maximum value for the n plus 1 derivative of f. Instead of doing that, I'm just gonna say that k is equal to the matrix A, right? Our original matrix. The reason why is that I don't really know how we can find a maximum value for this, right? I don't know how we can find that max. So I just said that, you know what, pick let's just pick the original matrix as our input for k. Now, once we do that, what we can do is use the formula, and we know that since we use a Taylor polynomial expansion until for 3 terms, we just replace n with 3, and we replace the value of k with this matrix right here, and we replace a with 0. Again, it would be 0 times an identity matrix, but it doesn't really matter here since it's just 0. And for the value of x, it's just going to be the matrix A, right? And simplifying this gives us this thing to evaluate right here, right? The main problem that you probably notice is this thing right here. How do we find the fourth derivative of f of A, right? The matrix A. How do we find that? Now, to evaluate that, we need to realize that the fourth derivative of f of x. Now, what was f of x? F of x was just e to the power of x. The fourth derivative of e to the power of x is just e to the power of x. Now, given that, we're just dealing with e to the power of a again. All we have to do is to basically to find the remainder right here, we need to evaluate an actual value, not an approximation, but an actual value for e to the power e to this matrix, right? And to evaluate e to the power of a, what we can do is utilize the concept of diagonalization, basically decompose a into these respective matrices where the matrix D is a diagonal matrix with eigenvalues in each diagonal entry, and then the matrix P contains the eigenvectors of the matrix A, right? So if we replace A right here with this decomposition, we can use the Taylor expansion again, right? You probably notice here the 2 by 2 identity matrix instead of 1 here. And then instead of x everywhere, we just replace it with p multiplied by d multiplied by p inverse, right? And then you probably notice that when we raise x to the nth power, right? Instead of doing that, we're actually just raising d to the power of nth power. And that is because of a rule of diagonalization, which is that if you raise a to the power to any power, then you raise the respective diagonal matrix D with the same power, right? We don't have to raise the matrix B and P inverse with the same power. We don't have to do that. Now, once we have it written like this, what we can do is actually factor out the matrix P and the matrix P inverse. So matrix P would be factored out from the left side, and matrix P inverse would be factored out from the right side. You're probably going to ask how can the 2 by 2 identity matrix, how can we factor out P from the 2 by 2 identity matrix? Well, just know that 2 by 2 identity matrix is just equal to P multiplied by P inverse, right? So since that is equal to P multiplied by P inverse, we can just factor out P, and then we can factor out P inverse. Now you probably notice here that in the center, this is just a Taylor approximation, I mean the Taylor polynomial for e raised to the matrix D, okay? And since we know that D is diagonal, the diagonal entries of D are raised to the kth power in each term of the series. Now, if this didn't make sense to you, that's okay. We'll cover that in the next slide. But just know that this thing right here in the center is just equal to e to the power of D. All right. So, yeah. So here, this thing right here is equal to this, and instead of just saying it's e to the power of D, I've actually just said that this is just a summation, right, with D involved in it. And this summation should evaluate to e to the power of D. Now, considering that we have ended up with this, coming from this to this is going to be challenging, right? It's going to require some thinking. Now, here's what I need you guys to do. For now, just ignore this part right here, right? The sigma notation and the denominator and factorial here. Let's just consider this matrix D to the power of n. What is D2? Well, first of all, what is D, right? D is a diagonal matrix. And we know that when you raise a diagonal matrix to, let's say, the nth power, what's going to happen is that the diagonal entries will also be raised to the nth power, right? So this matrix right here is just the matrix D, all right? And we know that D in its entries, D contains the eigenvalues of A. So sigma 1 right here and sigma 2 right here are the eigenvalues of the matrix A. And now that we've considered the matrix D, let's consider this summation right here with the n factorial. What we can do is just apply this operation to all of the entries in the matrix, right? And when we apply those operations to the entries right here where we have 0, nothing really happens because it's just 0, right? It gets multiplied by 0 and then it just disappears. However, once we apply these operations to the eigenvalues, we get something like this. We get this summation, right? And simplifying this, we notice that this summation right here is just equal to e to the power of the eigenvalue, right? Same thing here. The summation right here is equal to e to the power of the second eigenvalue. Now we're basically done here. We basically evaluated e to the power of a, right? All we have to do is find the eigenvalues of A and the eigenvectors to construct the matrix P, but that's going to take a lot of computation, so I just made your guys' lives easier and computed it for you. You're welcome. And so basically the matrix P is this thing right here, and the eigenvalues are 5 and 4. P inverse is this, and evaluating that, well, first of all, just as a reminder, as I've repeated many times, that the eigenvalues are sigma 1 and sigma 2, and the matrix P is made up of the eigenvectors. So here, this matrix right here, this column right here contains the first eigenvector, with 5 being the corresponding eigenvalue, and this right here is the second eigenvector with this corresponding eigenvalue, 4. However, when we evaluate e to the power of a by performing all those matrix multiplications, we get something like this, okay? And if we recall the original formula for finding the remainder, the Lagrange remainder, what we have done is basically found a matrix value, basically a matrix for this, matrix equivalent to this. And if we replace this with this, we get something like this. And simplifying the operations, we get something like this, right? The remainder of A, when we approximate it to Taylor, when we use a Taylor series to approximate the remainder, to approximate the value for A, f of A, we get the remainder of this. Now, what does the remainder represent? I don't know. All right, and I doubt anyone will be able to explain what this means. All right, the sake of this video was just to play around with two different concepts, and yeah, just to also explain you guys how diagonalization can be used to evaluate matrix, evaluate basically each of any matrix. So yeah, that was the purpose of this video. I hope you guys enjoyed. Thank you.